In this video we're going to have a look at the animation demo that's available within the demo package that was sent out. It's going to contain a reasonably simple form of animation, and we'll have a breakdown of the code in terms of how we're going to go about iterating through a sequence of images in a controlled manner to provide an animation. So the thing that we're interested in here is within the graphics package, and it's known as animation test fragment. Just as a reminder, the activity that is attached to is just the ordinary basic one, and all of the code that we're interested in having a look at is the one that we find within the test fragment itself. There's a few things within this, and as with the previous demos, I sort of stuck everything into the same class just for sake of simplicity. Of course, as a reminder, in a proper game you'd be separating these things out. So inside this particular demo, we're going to have our game world, and notionally our game world is simply going to contain, in this case, two animation objects that will update and will trigger their drawing to the screen. We will have attached to the fragment a view object, which we will be drawing them to. And again, as a way of emulating a simple game loop, we're going to invalidate and keep invalidating the view so it keeps on being redrawn. So we'll do that quite frequently. The other things in this, there's a little bit of on creation, where we're creating our game world, and on the on create view, where we create the view that we're rendering to. And then inside that, you have three inner classes, which really need to be in their own separate class, but as mentioned, they're just here for reasons of simplicity. We have an animation class. This is the thing we're really interested in. It's, if you like, the reusable piece of code that we can plug in to our different systems and then use this to drive animations. We will have our very simple game world that contains a couple of animations. And we will have our simple render view, which is a renderable surface with a little bit of invalidation to simulate a game loop running. Now, I might as well show you what it does. So if we're running this one here, it is the animation test. And if we fire the animation test up, you can see we actually have two animations happening on screen. We have one which is an explosion of sorts. And then we have a second one, which is a character running for a bit, then jumping. And we're cycling through both of those animations. So effectively, that's all that it does. The source images are down in the assets directory inside the image directory. So we have one animation 1 and the other one's animation 2. For animation 1, this is the explosion effect, so it's a total of 3, 6, 9, 12 odd frames within that. And you can see that each frame is of a fixed width. So as you go through the animation, each frame as sort of fades out towards the end, we're defining the same fixed width per frame of the animation. And that's going to be true for the other animation too. And in doing that, we simplify the process of being able to extract the frame of animation out. So here's the second one, where we have a character that stands still for a bit, then starts running for a bit, then will jump for a bit, and then we will repeat that particular segment as we cycle through. Again, we're dealing with fixed width frames here. The other alternative fixed width frame is you have variable width, where the characters would be packed more tightly together, and this would be the case if we're trying to maximize the amount of frames you got in one image. In other words, to minimize the amount of memory that it takes to store all of these things. But we're not particularly interested in that. We're going to make our life nice and easy in terms of the animation. So we'll have a look at this. We'll probably start off actually from the bottom and work our way up. So we'll have a look at the render view class first of all. So this is the thing that we are drawing to, and it also notionally contains our simple game loop, or how we're sort of simulating our game loop. Inside this, we're going to have a time. You can see that we're storing this as a long value, and we'll get onto that in a second, just in terms of how we are taking a snapshot of the time. We create this and we are having our reference time, our starting time is whenever we bring this thing into existence. And we're using system.nanotime. Now animations, same with the game loop, they are driven off time. Time is important. Particularly for an animation, we need to know when we change from one frame and move on to the next frame. So we want to have an accurate way of doing this so that if we're operating down in terms of milliseconds within the frame, we can be precise in terms of transitioning. So system.nanotime, built-in one, it's going to give, it's the most precise time that we have available. So it's going to give us the number of nanoseconds, and it's not going to be accurate down to the level of nanoseconds, but nonetheless it'll be very accurate at the level of milliseconds. And that's the mechanism, the vehicle whereby we will do our timing from. Now, everything that happens within this simply fits into the onDraw method. So this is where everything happens here. So for this particular view, whenever onDraw is called, and it's going to be called the first time we add the thing in to make it visible, we will set our canvas to be black. That's our background color. We're going to do a little bit of timing here where we get the current time. We subtract this from the reference time, and that works out how much time has actually elapsed since we last did anything. We turn that into an elapsed time expressed as a double. So for example, 0.02 seconds in that sense. So we're taking our milliseconds and converting them just into a normal floating point expressing seconds, and that's the way we're passing it in. And we update our reference time so that we sort of have taken a snapshot since the last update. We're going to remember a reference time for the next update, so we can work out that time then. We're going to a world, we're going to ask it to update itself, and then we're going to ask it to draw itself. When we do that, we're going to go to sleep for 30 milliseconds, and we'll repeat then this whole process because we are invalidating ourselves at the bottom. So you wouldn't actually want to do this in a proper game. I just stuck this in here. It's a sort of a simple, not particularly elegant way of sort of simulating a proper game loop, where we would have a separate thread of control that does the timing accurately and decides when we update our world and when we draw our world. But this is what we're doing for this simple demo. So that's the render view. For the game world itself, inside this, it's a very simple world. We have a couple of animations, animation 1 and animation 2. And again, as a little aside, for the purpose of this demo, that's where we put them in. It is probable in our game world we wouldn't have animations simply stuck in at this point. Our game world is likely to contain game objects. So we could have our character that you had there. That character could have a position, and one of the properties of that character object is that it might have a current animation. Likewise, we're likely to have an explosion object, for example, and that explosion object could make use of an explosion animation within it. But for reasons of simplicity, we're simply putting our animations directly into our game world. We create our world where we do our setup. If we're setting things up, we have to load in our bitmaps. So we have a bit here for loading in the animation 1 and the animation 2, and we use those then to save both of those bitmaps. Having done that, we then create our two animation objects. And when we're creating an animation object, you have to look at the constructor of this class. We pass in two properties. We pass in the bitmap image, and we pass in then the number of frames wide that animation is. Now that's presumptuous. It assumes that we have an image strip that has been passed in, and it is in horizontal image strip. It assumes that each frame within that particular strip is of the same width. And that is true for the two chunks of animation that we are using, but it is an assumption that we have made within this. So there's 12 frames for the explosion, there's 20 frames for the character standing, walking, and then jumping. Having created the animations, we then request that we play back those animations. And when we're playing it back, we give the, now again, this isn't an assumption here. For the two playback properties here, the first one is the duration over which I should play that animation. And the second property is, do I wish that animation to loop? So whenever it gets to the end, it goes back around to the start. And I've set up the play method so that these are parameters that you can pass in when you're playing the thing. Equally, for example, the period that you're playing it back, whether or not it loops, these could have been things that were passed in through the constructor, but it makes a little bit more sense, or having a bit more flexibility to have it defined here, because that, when you're playing it back, then you can control, for example, the playback speed. Though arguably, whether or not it loops is something that you maybe would want to put into the constructor. So give me an example on this. So we could say that we want our animation to finish, the explosion to finish in 0.4 of a second, for the character to jump to finish in, I don't know, 4.2 seconds. So if we were to push this out then to the tablet, we'll eventually see that the animation, the explosion then happens a lot more quickly, and the character running and jumping and moving is going to happen probably about twice as slow as it currently did. So we'll trigger our animation, and we can see then that the explosion is happening faster, and the character is running and jumping considerably slower. So we can use this here to control aspects of the playback. We have an update method in our world where we simply ask both of the animations to update themselves. So normally we'd be updating your game objects, and if a game object contains an animation, it would ask that object to update itself. We have a draw method, and down here when we're drawing it, so this draws directly to the screen. It doesn't involve anything fancy about viewports or anything like that. It's just draw the thing directly to the screen. So we are going to use two rectangles, a source rectangle, which contains the part of the image. For example, this image here that we want to draw. So if we were drawing the third frame, we would do the first, second, third frame, and we want to have a rectangle that would capture or encapsulate that particular bit of that overall image. So our source rectangle is going to contain the bit of the animation strip that we want to draw. The screen rectangle is going to contain the region of the screen, obviously, that we're drawing to. For the draw method itself, it looks similar sort of structure for each animation. We go to our animation object and we say, can we get out the source rectangle that holds the current frame of animation? And we'll have a look at how that works, but that'll be based on how long the animation's been playing, what's the appropriate frame for that point of time, and then working out what that frame is and returning it through that rectangle. The screen rectangle is hard-coded for both of these. So again, normally we would have an object, that object would have its position, it could move about on the screen, so the object would know whereabouts it is and could create its own particular screen rectangle then. Having done that, we draw it out. So we're going to the animation and we're asking the animation to give us the bitmap that it uses. We're using the source rectangle that the animation has worked out, and we're using the screen rectangle that we've specified, and we're not using any paint at the end, so it's just drawn as it normally looks. Do that for both of the animations, and that's it. That's what we get to see. So that's the setup and the configuration of all of this. So the final bit we're going to have a look at then is the actual animation class itself. And this is something that is actually sort of designed to be reusable, or you can sort of use it in different points. Inside this, the animation, we're assuming that the animation has a single bitmap that contains its data, and that's probably a safe assumption. You could go for more fancy things where animations may be split over multiple images, or it just depends on your source information. We have a get bitmap method which will return the frames, the whole image that we're drawing from, if we need access to that. And we then have frame width and frame height. Now this contains the width and the height in pixels of each frame of animation within our overall animation. So it is relative to our bitmap, where we will have the pixel width and pixel height of an individual frame within that bitmap. And we do that because it helps us calculate some of the locations. We have the frame count, which tells us for that particular bitmap just how many frames of animation we have within it. We have the current frame. So this will tell us which frame of animation we are currently displaying. So if it was, the very start of the animation, then the current frame, the index of that would be 0, which means we display the start of it, then we'll go into 1, then 2, then 3, as we play our way through the animation. Time is important, and we've got a couple of timing values here. First one, second of them here is actually the frame period. So this will tell us how long each frame is. So this is the full, how long each frame will be displayed on the screen in terms of the number of seconds associated with that. The frame timer then is going to tell us how long we have been displaying that particular frame for. So if each frame is to be displayed for, let's say, 1/10 a second, then the frame timer will tell us how far through that 1/10 of a second period, that 100 milliseconds period, we are. And whenever we get to the end, we exceed that 100 milliseconds, we'll go on to the next frame in the animation. We've got two properties here, Boolean properties, true or false ones. So if is looping, obviously tells us if this is an animation that when you get to the end, do you loop back around to the start or do you just stop? And is playing will tell us, are we currently playing that animation? And if we're not currently playing the animation, it means either it hasn't started or it has been set up not to loop and we play through to the end of the animation. So is playing basically lets us know if we're asked to update ourselves, well, do we worry about going on to the next frame? Okay, so the constructor then, and there is only one constructor here. You could put in different types that take in different properties and extend this out. But we pass in the bitmap and we pass in the frame counter that tells us the number of assumed frames within a horizontally striped bitmap containing our image data. We store this. We also store the number of frames. And we do a little bit of calculation then. So the height of the frame, we go to the bitmap and we say, well, how tall is the bitmap? For the frame width, we get the width of the bitmap and we divide that by the number of frames that we have within it. So it does make an assumption that we have a horizontal image strip. Here's the play method. And again, there's only one play method declared here. You could declare multiple different forms of play methods. This one here takes in the animation period. So this is how long in seconds that we should be playing the complete animation over. And then whether or not we are looping. So for the first one, we work out the frame period. So this is the total duration of the full animation from one end to the next, divided by the number of frames. And that will give us then the amount of time each frame should be individually displayed. We set our current frame to -1. Now we do this here because we're going to use this as a trigger later on for working out, have we just started playback of this animation? So whenever we do play, you'll see down when I'm looking at the update method, we're going to check to see, have we just commenced play? Is it just begun? And the current frame, if it has a value of -1, this is our way of signifying that playback has just commenced. We set our is looping to be whatever we said we wanted to be, and we set our is playing to be true because we've been asked to play. Update method then, this is where all of the hard work, so to speak, actually happens. We have a check initially at the start. So if we're not currently playing, then we simply return. We're not going to do anything, we're not playing, so whatever current frame is, that's the one we're going to be displaying. If we are playing, then we have a check down here to see if this is the first time that we have hit the update method following and is a play request. So again, this is where our current frame, we're checking to see, is it equal to -1? That's our trigger point. If that is the case, then we set our current frame, the index of our current frame, to be 0. So we are going to be displaying the first frame in our animation. And we set our frame timer to be 0 as well. So this basically resets the timer, which says as soon as you start playing it, okay, start with the first frame and then start from your frame timer from 0. And this will enable us then to make sure we trigger playback of that first frame, and we're monitoring how long we want to display it for. Having done that, we then add on to the frame timer the elapsed time. So this is the amount, and so for this one down here, this is our general case. So we'll be triggering this, if you like, most of the times we're going through this here. We'll only do this here once at the start, but in the general case, whenever we're playing it, we'll come in and we'll go to our frame timer and we'll say, okay, for the last frame, how long was that frame playing for? How much time elapsed from this frame and the last frame? And we add that onto our timers. This is our way of stepping through time for each of the frames. So that builds up one frame after the next. So let's say we're running at, say, 50 frames a second, so it's 20 milliseconds. We would be roughly adding on every single time we come into this. Eventually, after a number of updates, our frame timer is likely to increase to a point where it exceeds the amount of time that we've allocated for an individual frame. So if the frame timer is greater than or equal to the period of time we want to display a frame, then we want to do something about it. We want to consider, do we go on to the next frame? Do we stop our animation? What do we do? So if that is the case, we are increasing our current frame. We are saying, let's go on to the next frame in the animation. And we have a check to do here, because in going on to the next frame of the animation, well, we might have been on the last frame. So if we try to increment it by one, notionally we're going beyond the number of frames that are available. So we have a check here. So if the current frame is equal to or greater than the frame count, I mean, it's going to be equal to in terms of adding the thing up. Greater or equal to is just a way of putting it more safely. This means then that we have notionally ended. We've got to the end of the sequence of frames, and we check to see, are we looping? If we are looping, then our current frame gets to be reset back to the beginning frame. So we will jump back to the start of the animation and commence playback again. If we are not looping, we've got to the end, then effectively we set our current frame and our frame count and everything to be -1. We say that the animation has finished, there's nothing to be displayed, and we set is playing to be false. So this is our way of cleaning this up to say that, okay, nothing needs to be done, the animation now actually has concluded. Down here, so this is still within our if the frame timer is greater than the frame period. The last thing that we want to do is to reset our frame timer. Now, we don't set it back to 0 to signify that we have gone into a new frame. Instead, we take away the frame period. And the reason we do that is that we're unlikely to exactly hit our frame period. We're likely to be a bit beyond it. So we want to take that error, if you like, into consideration. So the frame timer will take away whatever the frame period is. So it'll be reset to something close to 0, which takes into account just how the overshoot that we had for the current frame. And that helps make sure that we actually do keep on schedule, so that if we want to do the animation in 2 seconds, we will actually complete the animation in 2 seconds. And that's more or less it. It's quite straightforward and simple in terms of the timing mechanisms. The get source rectangle then, so this is the method that will return the rectangle that we use in the animation to be drawn out. And we have a check here if current frame is equal to or greater than 0. Now, the only case that will not be true is if it has a value of -1 in the code above. And it has a value of -1, it sort of signifies that, you know, we're just about to start playback, or playback has finished and we're not looping, in which case we set it back to -1. So this is a small check to say that we're only going to worry about updating the source rectangle if we have a valid frame associated with this and there's something that we're playing. If we do, then our source rectangle, we're setting this equal to the current frame times the frame width. And that makes sense. So if it is the current frame is index of 0, then we're going to start from 0. Otherwise, if it's 1, then we will start from 1 times the width of the frame. If the index is 2, then 2 times the width of the frame, and so on. 0, we're assuming that our starting Y coordinate is going to be the top of the bitmap, so 0 is the image for that. Where we draw 2 then is current frame times frame width, so that's the same as what we had above. I'll just move it down here. So there's no difference to this particular bit, except we are adding on one frame width across. So we are going a frame width across in terms of our ending x coordinate, and from 0 down to frame height in terms of our ending y coordinate. So that will give us a frame width by frame height chunk from our source bitmap, which corresponds to the particular frame of the animation that we are working on. And that is the end of that particular class. So it has an update method and has a get source rectangle method that returns the region that should be drawn. But it sort of assumes that some other process will go to it and will ask what region needs to be drawn, and will then determine whereabouts it happens to be drawn on the screen, which is what you normally want to have happen for an animation. So it is nice and straightforward, nice and simple. You can take the animation class that we have here, you can make it more fancy, you can add in different types of configuration options. Some of the demos that students have submitted in the other years, you do want to get into a situation where you have an object, or it depends on the game, where you have a class which has multiple different types and forms of animation. The one we had of the character, this one here, had the character notionally standing, had a running, and had a jumping animation, all stuck within one particular image sequence. Now, really, there's 3 different types of animation within that in terms of the idle, the running, and the jumping. So a more fancy, more sophisticated manager would be able to go into a large sprite sheet. It could be horizontal, it could have horizontal rows and columns, and to be able to take out different parts of that and to be able to trigger playback of a number of different types of animation. So this is a fairly simple implementation, and there's lots of ways you can make it more fancy or more capable.